I'm your host, Chad Papa, and I currently serve as a research assistant with the Forest Carbon and Climate Program, as well as I'm a PhD candidate in the Department of Forestry at Michigan State University. First off, I would like to give a quick thanks to our co-host, the Society of American Forest, or SAF. SAF is the national and scientific and educational organization representing forestry and related natural resources professionals across the United States. Founded in 1900, SAF promotes science-based, sustainable management and stewardship of the nation's public and private forests. For today's presentation, Grant Domke from the U.S. Forest Service will be discussing trees and forests as nature-based solutions in the United States. Grant currently serves as a research scientist and leads the carbon science group in the Forest Inventory and Analysis Program within the United States Department of Agriculture Forest Service. Grant studies how carbon cycles through forest ecosystems in the U.S. using strategic level forest inventory data and auxiliary information. He leads the team responsible for compiling estimates of the land base and greenhouse gas emissions and removals in forests, woodlands, and harvested wood products each year as part of the United States commitment to the United Nations Framework Convention on Climate Change. Grant has also served as a lead author on the 5th National Climate Assessment, the 2nd State of the Carbon Cycle Report, and the Intergovernmental Panel on Climate Change Guidelines for National Greenhouse Gas Inventories. Before we hand the reins off to Grant, we have a little bit of housekeeping here. I'd like to briefly share a few details. To automatically receive registration details and information regarding upcoming webinars, please join our mailing list by scanning the QR code on your screen or by emailing forestsc@msu.edu. A recording of this session, along with a copy of the slides and any supplemental resources, will be posted to our site following the presentation. And then as well, after this presentation, we will have a Q&A session. You can use the chat or Q&A function at the bottom of the Zoom interface to submit your questions at any point during the presentation. We will do our best to address as many questions as possible. If you are calling in on a phone but can email, you can also send questions directly to forestsc@msu.edu. And now I will drop a link in the chat as well to sign up for the Forest Carbon and Climate Program mailing list. Last thing of note is attendees are qualified to receive CFE credit from SAF. The credits will be automatically applied if you register for the event with the email associated with your SAF account. Similarly, attendees are qualified to receive CEU credits from ISA. Please email the forestsc@msu.edu email address with your CERT ID to receive those credits. And with that, I will hand it over to Grant. Thank you, Grant, so much for sharing with us.
Thank you, Chad. I'll go ahead and share my screen now. All right. So thanks very much for the opportunity to participate in this learning exchange series. It looks like a fantastic series, and you have many fantastic speakers in the weeks ahead. So today, as Chad mentioned, I'll be talking a bit about how trees and forests in the United States can be thought of and really are nature-based solutions to climate change, as well as a variety of other risks in the United States. Before I do that, though, I need to acknowledge that the work that I'm going to be talking about today happens within a much larger group. And we have several Forest Service cooperators, university and agency cooperators that contribute to a lot of the research and reporting activities that I'll be describing. And most of all, I need to acknowledge the fantastic work by Forest Inventory and Analysis field crew members who collect the all-important data that are used in a lot of the research activities and reporting activities that I'll be describing today. So with that, we'll go ahead and get started. So carbon dioxide is Earth's most important greenhouse gas, a gas that absorbs and radiates heat. Unlike oxygen or nitrogen, which make up most of the atmosphere, greenhouse gases absorb heat radiating from the Earth's surface and re-release that in all directions, including back towards the Earth's surface. Without carbon dioxide, the Earth's natural greenhouse effect would be too weak to keep the average global surface temperature above freezing. And by adding more carbon dioxide to the atmosphere, humans are supercharging the natural greenhouse effect, causing global temperature to rise. You've probably all seen this sort of hockey stick curve or something like it, where either you see the global surface temperatures, or in this case, CO2 concentrations in our atmosphere. And this particular Keeling curve, if you will, shows sort of the point of around the Industrial Revolution in 1750 and how CO2 concentrations have increased since we began burning fossil fuels. You can see this record has been reconstructed thanks to ice cores. And then around the early 1950s, we began using or relying on observatories, particularly the Mauna Loa Observatory, where the data you see here really from 1950 to present is documenting that sort of interannual, the seasonal patterns of CO2 in our atmosphere. The most recent reading, 420 parts per million, is much higher, of course, than pre-industrial levels. And why is that important? Again, as I just noted, there is this sort of correlation between CO2 concentrations in our atmosphere, the blanket effect that this causes, and global surface temperatures. You've probably seen these heat stripes in a variety of formats. You even see them on t-shirts now. This is the trend in atmospheric CO2 versus global temperature. And included in this nice graphic are also some recent high-level climate summits, if you will. You can see that there's been much work to sort of coordinate on this topic of atmospheric CO2 and the concerns around increases in global surface temperature. But we have a lot of work yet to do. And so forests have been targeted as one potential solution to combating climate change and increases in CO2 in our atmosphere. And that's what we'll be talking about today. We also know that these increases in CO2 concentrations and the associated increases in global surface temperature are wreaking havoc around the world. There's not a corner of the planet where people are not in some way impacted negatively by these increases in CO2 and associated global surface temperatures. This is from the 4th National Climate Assessment, and just a shameless plug that the 5th National Climate Assessment is going to be published in the weeks or months ahead. Sometime this fall, you can look for the National Climate Assessment, where you'll see updated graphics similar to this one, which document the role of climate in the United States and the various patterns and changes and effects on ecosystems and people in the United States. What this graphic's really showing is just some of the things that have changed as a result of increases in CO2 concentrations and associated global surface temperatures. We're seeing increased temperature, obviously, longer, persistent, and extreme heat waves, increases in sea level, greater precipitation events and changes in the patterns of precipitation, declines in snowpack in the western U.S., increases in drought conditions in some areas, particularly the West, and then a whole variety of other things that are wreaking havoc, not just on land, but also in our oceans. So as part of the U.S.'s commitment to the United Nations Framework Convention on Climate Change, in the early 1990s, we agreed to compile an annual inventory of greenhouse gases, and particularly greenhouse gas emissions and removals. There are 6 major gases, and we report those on a long time series beginning in the year 1990, and that time series extends to 2 years before present. This sort of national policy instrument or international reporting document is really designed to be sort of a barometer of how the economy in the United States is doing in terms of our emissions and removals. And this graphic here sort of illustrates by major gas over this time series how our emissions and removals have changed over time. So number one, you can see that carbon dioxide is absolutely the largest contributor to greenhouse gas emissions in the United States. And from here throughout the rest of this talk, you will see positive and negative numbers. When I show positive numbers and I'm talking about a flux or a change, That represents either a transfer to another category, and one of those categories is the atmosphere. So any these positive numbers here, there's around 5,000 million metric tons of CO2 equivalent emitted annually by all sectors of the U.S. economy. They're also major sources of methane and nitrous oxide. Relative to CO2, the emissions are small, but the global warming potential of those two gases are substantially higher than CO2. And so the overall net effect is quite large. You'll also see here that the purple below that zero line represents the land sector. And so the land sector is actually a net sink. We're removing more carbon dioxide and other gases from the atmosphere, but primarily carbon dioxide from the atmosphere than is being emitted back to the atmosphere. Some important sort of points from this time series. In 2021, net emissions increased by about 6.8% over 2020 levels. In 2020, we had this large decline or dip as a result of the global pandemic, where we weren't driving as much. Manufacturing slowed or stopped in some cases. Cement production slowed or stopped in some cases. And so some of these major sources of emissions declined during the global pandemic, and as a result of stay-in-place orders and other things associated with the pandemic, we saw a large decline relative to the year 2019 in the 2020 emissions. Things have rebounded slightly in 2021, and we're in the process of compiling estimates for 2024, which will go through 2022. So we'll be able to evaluate how this trend continues. Does it go up or down? What's the directionality of that trend? The other important point here is that there are a lot of agreements out there. 2024 is the first year of the global stock take, and the national greenhouse gas inventory in the United States will be the US's official submission to the first global stock take. We are evaluating our contributions or our emission reduction targets relative to the year 2005. And so in this graphic, we can sort of ask the question, well, how well as an economy in the United States are we doing in terms of our emission reductions targets? Well, based on the year 2005 through this 2021 time series, net emissions have declined or decreased by approximately 16%. Now, how is this relevant to recent U.S. commitments? So I just acknowledged the 2024 global stock take, which really spawned from or was the result of the 2015 Paris Climate Agreement. And here are the U.S.'s targets for emissions reductions. And our first sort of submission several years ago, we wanted to reduce emissions by 17% below 2005 levels by the year 2020. And then more recently, in 2015, when we submitted our nationally determined contribution, we endeavored to reduce emissions by 26 to 28% below 2005 levels in 2025. Moving forward now, when we re-entered the climate agreement under the current administration, we made even more ambitious targets to reduce emissions by 50 to 52% below 2005 levels by 2030. And so how do we get there? How do we do that? Well, it's going to require all sectors of the economy, including the land sector. And that's where nature-based solutions come in. So what the heck are nature-based solutions? We hear these thrown around, and this term thrown around a lot. It goes beyond just climate. And really, there are a few key words that I pull out of this sort of original definition of what a nature-based solution is. They're really designed to protect, manage, and restore ecosystems that address societal challenges. And what are some of those societal challenges? Well, there are many, not just climate change. That's really the focus today in this talk, but also disaster risk reduction. So how can we mitigate those disaster risks through nature-based solutions? Food and water security, health, and all of these we know are critical to economic development. There have also been a whole number of studies evaluating globally and even domestically the role of natural and working lands or nature-based solutions in terms of combating this problem or mitigating CO2 emissions. And so there are a whole number of studies that we can evaluate and look at. And many of those studies have targeted and identified trees and forests as being among the largest contributors to some of the solutions in this solution space, if you will. So why is that? This is kind of a new slide for a talk like this. As a carbon scientist in the FIA program, I've long just sort of made this assumption that people understand how, the constitution of trees and what they're made up of. But increasingly, I'm learning that it is more complicated than that, and that it's maybe not as obvious as I've thought it is. So if you think back to sort of grade school, when you maybe first were introduced to this idea of photosynthesis, it's really live vegetation interacting with the atmosphere through photosynthesis to convert this sort of sugars or carbohydrate into woody material, woody tissues and other tissues for structure and a variety of other anatomical features within trees and really live plants in general. So it's through photosynthesis that trees and vegetation more broadly, live trees, are interacting in a positive way with the atmosphere, removing carbon dioxide through photosynthesis, storing that in these different tissues. And for example, woody tissue carbon concentration is around 50% of the mass of that individual tree. It varies quite a lot, and that's what this graphic here is showing, that there's quite a distribution of the carbon concentration around different species, and it varies even by live and dead status. And if you really want to get specific, it even varies by component and by sort of stage, sort of life stage of the individual species or specimen. So that's really why we think about trees and carbon when it comes to climate change mitigation. They're actively removing carbon from the atmosphere, storing them in different structures. And then that carbon even cascades through that forest ecosystem and accumulates not just in live trees, but as those live trees die, the carbon doesn't go away oftentimes. It may be transferred to the deadwood pool or the litter pool or end up in the soil carbon or in the soil organic material. So forest ecosystems can accumulate this carbon that they've removed from the atmosphere through photosynthesis in a variety of live and dead organic matter. And so that's really what I'll be focusing on for the rest of this talk. So this is a similar time series to what I just showed, but this really zeroes in on those purple bars from that earlier graphic. This is just the land sector now and shows the contribution of the different categories within the land sector to emissions and removals in the United States and the overall carbon budget. And you can see here by the black line that it's below the zero line. So overall, as I mentioned earlier, the land sector is a net sink. And it's a net sink thanks in large part to forests. So forests are a substantial component of the land sector, represent about a third of the area, which we'll talk about in a minute. And overall, between urban trees and settlements, that's the trees part of this talk, as well as land converted to forest land and forest remaining forest land, the trees and forests in those categories combined with harvested wood products, so carbon transferred from those forests into short and long-lived wood products, represent more than 95% of the sink strength in the land sector. So a really large and important part of the US carbon budget and frankly, the global carbon budget. To show that another way, so this is a similar sort of cartoon just for the year 2021. So the last bar in that time series, you can see that overall forests are a net sink of about 785 million metric tons of CO2 equivalent. And there's a lot of movement of carbon happening throughout this ecosystem. So the net ecosystem exchange is around 592 million metric tons of CO2, as well as some additional contributions from land conversions, which increases that number. And then urban trees are removing carbon from the atmosphere. And there's some transfers of carbon from forests into harvested wood products. And some of those products in that pool decay and or are burned. And so there's some carbon that's removed from the atmosphere. Overall, the forest land categories, including harvested wood products and urban trees, offset the equivalent of about 13% of our annual economy-wide greenhouse gas emissions each year. So they're really an enormous contributor to emissions offsets, if you will, or the overall net emissions to the atmosphere, what the atmosphere sees. And what is that in different terms? Something that we can all relate to. Well, that's the equivalent of about 175 million passenger gasoline vehicles in the US. And there aren't 175 million passenger vehicles. They're right around 105 million. So that just gives you a sense. 210, the emissions from 210 coal-fired power plants for 1 year. So the contribution of forests right now are really substantial in terms of the offsets or the overall contribution to net emissions, what the atmosphere sees. Now I'm going to pivot a little bit and talk about some of the methods that are used to compile those estimates and really drill down on the various components that make up this forest land category more broadly. And to do that, I need to provide a brief overview of the FIA program. So that's where I sit in the USDA R&D. So the Forest Inventory and Analysis Program is really designed to specifically track change over time. There are permanent sample plots across all lands and ownerships, and those plots are remeasured. All those plots that have at least one forest land condition, so classified as forest land using remotely sensed information, are remeasured every 5 to 10 years. It's using these remeasurements that we can start to get estimates of carbon stock changes and also attribute those changes to particular drivers. There are multiple approaches for assessing those disturbances, both natural and anthropogenic, and tree and site level attributes are collected. So we measure and we actually classify damage, mortality, as well as removals on individual trees in the database, really allowing us to zero in on what's leading to changes in growth, either increases or decreases, but also damage and mortality, and also track removals that are then used to compile estimates of the transfers to the harvested wood product pool. We observe both land cover and land use on these plots, and not just the forested plots that field crews visit in the FIA program, but also those non-forest plots for all the other land uses, which become really important as we think about land conversions and the role of carbon dynamics associated with those conversions. All of these data are publicly available and accessible in several different formats. And it's important to note here and kind of remind yourself throughout this talk that the FIA program and the FIA National Forest Inventory is not a carbon or greenhouse gas monitoring system. And so there have been decades worth of models and methods developed to leverage this National Forest Inventory and the data collected as part of this national inventory to turn that into information useful to estimate carbon stocks changes and more broadly greenhouse gas emissions and removals. So this illustrates for the 50 US states as well as the Caribbean islands, the distribution of forested plots in the US. There are around 141,000 forested plots in the US, and that's at one point in time. Those are all the annual plots, which are remeasured again every 5 to 10 years. 5 to 7 in the east and west of the Mississippi, approximately west of the Mississippi, every 10 years. And more broadly, there are about 350,000 total plots across all lands. You can see in some cases there's states that are darker. In those states have bought down or recently intensified their sample. So where is the forest in the US and who owns it? Well, you could kind of get a picture based on that map of the distribution of forested plots. But this is another sort of illustration at 30-meter resolution of the forest land in the conterminous United States and who owns that. So two very different patterns of ownership in the US. In the eastern US, a family and really private forest land is most common, again, made up of corporate and non-industrial forest land owners. In the West, a very different story. Most of the forest land in the Western United States is publicly owned. And that does have some influence on forest carbon stocks and stock changes. Here you can see just broadly breaking things out by public versus private ownership. A few things that really jump out to me in a graphic like this, and this is based on the most recent greenhouse gas inventory, is that, across about 300 million hectares of forest land, about 80% of the sink strength is thanks to the private forest, the forest land in the southern United States, and much of that forest land is privately owned. You can also see the various contributions by other regions, public versus private here. The North has a tremendous amount of private land, and that forest land is contributing substantially to the sink as well. You will also note this pattern in terms of like an overall increase in carbon stock changes on private forest lands and a decrease on public forest lands. So again, ownership matters, and understanding why these carbon dynamics look so different on these different ownerships is quite important. And of course, it varies by region. In particular, in the Rocky Mountain region, again, where most of the land is public, you'll see that those bars are above the zero line. And so most of the states in the Intermountain West or Rocky Mountain region are actually losing more carbon annually than they're gaining. So they're net sources of carbon. And there are a whole bunch of reasons for that, and we'll get into a few of those in just a minute. So another way to look at this, besides just by ownership pattern, is at that individual tree level. So what is the contribution of individual trees here? And this is a high resolution map by region, looking at the carbon density. So per unit area, how much carbon is stored in live trees. And so the darker the green on this map, the higher the biomass or carbon. And in some cases, it even goes into purples. Not surprisingly, for those of you on the Pacific coast, you're well aware that the forests in the Pacific coast store a tremendous amount of carbon, not just in the live trees, which is illustrated here, but also in the deadwood and soil organic matter pools. So a lot of the carbon in live trees anyway is concentrated in that Pacific coast region, but also along in the Appalachians, especially the southern Appalachians, as well as the northern lake states. Now let's take a broader perspective and look not just at individual tree carbon, but look at the distribution of total forest ecosystem carbon across the United States, the conterminous US, by US county. The exception here, I'll just flag it, and I've got a note here, Wyoming, we're still not able to disaggregate by individual county just based on the way we compile things in the greenhouse gas inventory. So you'll see the entire state there. But otherwise, we break everything out in every other state by individual county here just to illustrate where the carbon density is across the ecosystems. And very similar to what you saw in that previous graphic, here at the county level or jurisdictional level, you see that much of the carbon in the United States, the carbon stored in forest ecosystems, is along the Pacific coast, the northern lake states where there is rich, deep organic soils, as well as the northeastern US and throughout the Appalachian region. So we provide this kind of information in a variety of different formats in the FIA program, including as part of a resource bulletin that's published each year. This resource bulletin includes not just summary statistics and graphics at the national scale, but there's a companion research data set for each US state, which includes all of the associated pools, just like we show here. So you can understand the contribution, at least from a carbon stock and stock change perspective, by pool of each of these different ecosystem components. Now, it's important for context and magnitude, or it's really important to understand the magnitude between carbon stocks and changes. So I just showed you a map of carbon stocks in the US, and we can't conflate carbon stocks with carbon stock changes. This quite literally, this is a little snapshot or a pie, a piece of a larger circle. That pie or that piece of the circle represents total carbon stocks in the United States. And this dot here represents the stock changes each year. So I include this for a couple of reasons. Number one, to remind myself that, hey, this stuff is complex. We're dealing with really large stores of carbon in the forest, where there's almost 300 million hectares of forest, and carbon is stored across a whole variety of ecosystem components within those forests. And then to really tease out annually how those large stocks are changing can be challenging. But it's also important to wrap our hands around those changes and attribute to the extent we can why they're changing, so that we can inform management activities and policymakers to sort of develop, policy and practices that maintain, if the goal is to maintain or enhance carbon stocks where possible, particularly in a talk like this where we're focused on mitigation. So with that context, now that you've seen the picture of carbon stocks, this is that same map by jurisdictional, by county, looking at carbon stock changes. So in this case, if it's a negative number, that represents more carbon being removed from the atmosphere each year than is being lost through decomposition, transfers to another category, or back to the atmosphere. So you can see, again, there are some similar patterns. The Northern Lake states, the northeastern US and the Pacific coast jump out, as well as that sort of wood basket of the southern United States as being major sinks by county. But you also see now some brown in the Intermountain West, where those counties represent net sources of carbon, where there's more carbon being lost to the atmosphere than gained in those individual counties on an annual basis. And so what is the reason for that? Well, to begin to understand the reason, we need to start to disaggregate things by state or by region and by ecosystem pool, so we can start to make sense of some of this. So where you see dots here above that zero line, in the same way you've seen it in other time series, now just showing things by state, you'll see that those dots above the zero line have a large brown box beneath it. And in many cases, what that's illustrating is that we've got substantial mortality of live vegetation, which is being lost or transferred to the deadwood carbon pool. So a lot of carbon is being transferred from live to dead, and there's not as much capacity in those forests, particularly in the western US, where we've got wildfires and drought and insects and disease and complexes of all of those things, as well as other drivers of change, contributing to changes in live and dead tree abundance, and where you're seeing fewer and fewer live trees and more dead trees, where a lot of that carbon might still be stored there. So there are still high carbon stocks in some cases, but the capacity of those forests, because there aren't very many live trees in some cases, to sequester new carbon from the atmosphere are limited. And you're starting to see more carbon being lost through combustion and wildfire or decomposition than is being removed from the atmosphere and the remaining live trees. Just a few words on trees and settlements. So that's another important category that contributes in a really meaningful way to the US carbon budget. Trees and settlements account for greater than 17% of the total land sink. And that sink strength has increased. And that's kind of a double-edged sword. Part of the reason we're seeing that sink increase is because we're seeing land change from natural and working lands in many cases into this settlement or urban category. And so those settlement category, that might mean a loss of carbon in another category and a gain in carbon in the settlement category. So it is important to dig in a little bit here and understand why we're seeing the increases. But there are a lot of urban forests that continue to grow and sequester carbon in much the same way as rural environments. And so put another way here, these urban trees and forests and settlements account for greater than 25% of passenger vehicle emissions each year, are the equivalent to, if you will. So now that we've talked a bit about and laid sort of the groundwork or foundation for what's driving changes, both the sink, increases in our sink or decreases in our sink, and particularly by region and ownership, let's turn now and think about what's contributing to those changes in forests. So some work actually led out of MSU and Andy Finley's lab found that the abundance of the most common tree species in much of the western United States is changing. And those changes are driven in large part by disturbance. Fire, insects, and disease are all major contributors to changes in the relative tree density in the western US, looking over two measurements and all of the annual inventory data in the western United States. So a clear signal that disturbance, particularly natural disturbances in the West, the frequency and magnitude of those disturbances changing, in part exacerbated by climate, are leading to changes in the abundance of tree species and those most common and important tree species in the Western US. To sort of build on that, a national analysis looked at the role of insects in disease on carbon sequestration capacity, we were calling it. So, what is the rate of annual uptake? And what we found here was that plots with evidence of insect damage were sequestering on average about 68% less carbon per unit area than plots with no evidence of disturbance. And plots with evidence of disease, individual trees with evidence of disease, were sequestering on average about 32% less carbon per unit area than plots with no evidence of disturbance. And so we see even these sort of diffuse disturbances and native insects and disease are contributing to declines or reductions in the capacity of forests to sequester and then store carbon, which is contributing to some of the reasons that we're seeing these forests in the Western United States transition from sink to source or persist as net sources of carbon. Other reasons for change, demographic drivers of change, they're not all abiotic or not biotic, unless you consider humans. So in some cases, we're just seeing land change. Every year, there are around 1 million hectares of land that move in and out of forests. And so those land conversions lead to loss of forest land. And when there's a loss of forest land, maybe some of that carbon, for example, the soil carbon, might get transferred into a new land category. But oftentimes there are removals and loss of a lot of the ecosystem components that store carbon and accumulate carbon over time. And so land change has been a real problem in terms of losing forest land. And there are some predictors or obvious predictors of land change. So water edges, forest land adjacent to cities or urbanized areas, and a variety of other things that are sort of really, there's some hotbeds for probability of land change. And so looking at that, and really, this is just a reminder to me that maintaining, and a plug for maintaining forest as forest, is where we need to start. And once we get there, then we can start thinking about how we might enhance or supplement those forests to enhance their capacity to sequester and store carbon. And then finally, just to sort of take this beyond the United States, there have been several recent studies looking at the role of natural disturbances and human interventions in changes in standing carbon and overall net fluxes. And a lot of the same patterns that we see in the United States and reasons for declines in the sink strength globally can be attributed to some of the very same drivers of change. Things like forest fire, for example, are major drivers of change in the US as well as the globe. And just thinking about that a little bit more, this is the same time series, 1990 to 2021, where we show the area burned in the gray bars, and then the associated CO2 emissions and non-CO2 emissions. The non-CO2 emissions are nitrous oxide and methane here. So you can see that not surprisingly, CO2 and non-CO2 emissions track with the area burned in the United States. And this is area in the conterminous US as well as Alaska. And you can see there is a trend over this time series of increases in the area burned and concomitant increases in the CO2 and non-CO2 emissions associated with those areas burned. I don't have to say it, you've probably all seen it, that this year has been unprecedented, particularly in Canada. The emissions they're experiencing are orders of magnitude larger than anything they've experienced before. And so, this pattern is not just the United States, but we're seeing it just in adjacent Canada, that some of the largest burn areas on record are occurring in the recent time series. Thinking about post-fire or post-disturbance and recovery, are forests recovering in the same way they have historically? particularly under, increased, the frequency and severity of fire, for example, is changing in part due to climate change. Are we seeing forests recover in the same way? So looking at the dense time series of Landsat, we actually tracked reforestation recovery of tree cover. And what we found was that early in the time series, beginning in the 1980s, we were gaining forest, but sort of this tracks really closely to that previous graphic around CO2 emissions and area burn, starting in around the 1990s. And really since then, we've seen recovery slow, and we're actually seeing more loss of tree cover and delayed recovery than we are seeing gain. And there are a variety of mechanisms and I think tools out there to continue to track that to help us understand where we may need to intervene or supplement those conditions to help in their recovery. So with that, I'd like to close with just a couple advances. So I've documented all the things that forests can do for us from a sort of national perspective and their role in climate change mitigation and offsetting emissions from the US economy. We continue to strive to improve the methods and models that we're using to estimate and report on the contribution of forests in this space. And to that end, I'm excited to announce that new volume biomass and carbon models were adopted in the public-facing FIA database on Friday. So if you were to go to that database today, you've got new estimates for live and standing dead trees. And that led to some changes in the litter methods that we used. There are also new litter and soil models adopted. What does that mean for estimates that you would see if I were to give this talk in a year's time? Well, those methods, which I need to acknowledge, led to structural changes. So nothing biologically changed on the landscape due to these change in methods. But those methods better characterize the various tree components, particularly tops and limbs. The previous methods and models used to characterize biomass and carbon in particular weren't as robust as these current methods to characterizing component biomass and carbon. And what we're seeing overall is about a 9% increase nationally in total standing stocks and about an 11% increase in stock changes, which can be directly attributed back to this structural change, this methodological change from what we called the component ratio method for biomass and carbon estimation in live and standing dead trees to this new method known as the national scale volume and biomass models. These new models were fit, the volume models were fit with more than 280,000 observations of volume, 30,000 observations of biomass, and new carbon fractions that are species specific. All of these new methods will be documented in this forthcoming GTR and are available in a website noting state by state the kind of changes you can expect from these new methods. Some other advances that you can see in the 2024 greenhouse gas inventory, which has just been submitted for expert review. We extended the conterminous US methods to coastal Alaska, which improves the consistency and continuity in our reporting. We've included for the first time in the 2024 inventory, Hawaii, Pacific affiliated islands, which includes Guam, Northern Marianas Islands, and a few other islands in the Pacific, as well as the Caribbean, both the U.S. Virgin Islands and St. John's, and Puerto Rico, and some other improvements. Litter and soil model predictions, which we've used in the greenhouse gas inventory for about 5 years, are now in the FIA-DB, and we're part of that national scale volume biomass push. So there's continuity and consistency between what's in the public-facing FIA database and what's in the greenhouse gas inventory. We've improved consistency in some of the official representation of land by reconciling some difference between large data sets around cropland and grasslands. And finally, our group is responsible for compiling fire emissions estimates. And we've updated some of our methods using a variety of data sources, monitoring trends in burn severity, really contemporary MODIS data, so near monthly MODIS data, and then YFIGS data, as well as these YFIGS, these these geospatial inventories and monitoring trends and burn severity data, estimates are now calculated per burn. So we're actually looking at fire perimeters, understanding the fire intensity within those fires, and identifying the forest within those perimeters on a forest by forest basis to compile estimates of fire emissions as part of our reporting. So with all of that, nature-based solutions need to be considered as part of a portfolio approach to climate change mitigation. As I've just illustrated, trees, forests, and harvested wood products represent some of the greatest opportunities in the United States and really the world over to combating climate change and some of these other risks to humanity. There are real opportunities in the US and beyond to enhance carbon sequestration capacity, but we really need to think locally about where that we do that and make sense, and whether it makes sense based on the communities, the disturbance patterns, and how things are changing. There are real opportunities to avoid emissions in some cases based on understanding of the risks of those disturbances and how we, approaches to make ecosystems more resilient. We can leverage substitution of fossil fuels by utilizing harvested wood products in different ways to substitute for more fossil fuel intensive products. And finally, we need to think about this as more than just carbon. So this is a carbon talk. I'm a carbon scientist, and we're talking a lot about climate change, but really we need to think beyond carbon and what are the roles of these things, these forests in terms of their ecosystem goods and services that extend well beyond carbon and climate change mitigation. And finally, we really need to be realistic and work with nature and consider all lands and peoples as we think about mitigation and adaptation solutions to combat these problems. With that, a quick thanks. My coordinates are here, as well as several websites where you can find all of those publications cited throughout this talk, a website dedicated to the national scale volume biomass models, and one more shameless plug for the forthcoming National Climate Assessment. Thanks a lot.
Thank you so much for your presentation, Grant. That was great. I think everybody here probably learned a lot. And so with our remaining time, we're going to move to our Q&A portion of the webinar. We've been monitoring the chat feature and the email, and we'll start with some of those questions, but please remember to submit your questions in the chat box or by email to forestc@msu.edu. So with that, I have a few questions. I think to start off is, how do we account for greenhouse gas emissions from logging, trucking, and manufacturing of harvested wood products when we account for emissions in the land sector?
Yeah, really good question. So everything that I just described focuses on just the components that are removed from the forest. So we are focused primarily on just that wood and the primary and end products that result from the wood. The emissions associated with the manufacturing of that wood, the transportation of that wood, and the burning of that wood all fall into different categories and within the greenhouse gas inventory. So whether it's the manufacturing of those materials, that would fall under manufacturing. If it's energy, those would fall under energy. Although in the case of energy, if we know that wood is being used as fuel, it's considered instant oxidation, and that removal from the forest is considered an immediate emission back to the atmosphere. In the case of transportation, there's a transportation sector. So I know that's probably an unsatisfying answer. And for this particular question, where you can see multiple sectors of the economy sort of overlapping here, trying to get a picture of what the total emissions and removals are, like sort of a life cycle assessment of this. In order to do that in sort of an instrument like the greenhouse gas inventory, you really need to tap into a variety of different sectors to actually extract all of that information to get a picture of the total emissions profile from the various components of the sector.
So we have another question here. Could you briefly comment on how potentially managing our forests solely for increase in carbon storage could be at odds with other types of forest management, or maybe just think about some of like the trade-offs between managing for carbon storage versus other ecosystem services from forests?
Yeah, well, I hope you don't take away from this talk that that's what we should be doing. So carbon is really sequestration, but also storage are a few potential objectives within this broader suite of goods and services that we must consider as part of forest ecosystems and the sort of those services that humanity enjoys from forests. They are at odds. In some cases, it does not make sense to maximize carbon. For example, in fire prone ecosystems, it may actually make sense to reduce the amount of carbon that's on the landscape in the name of maintaining some carbon in those forests and also maintaining some of the other ecosystem goods and services, whether it be aesthetics, recreation, wildlife habitat, water quality, you name it. We need to be thinking about the role and decisions that we're making. Where does it make sense to prioritize carbon sequestration and or storage? And how might that interface or interact with other ecosystem goods and services that local economy and community rely on? And when you do that, that's kind of why I ended that with that final slide where we must consider all land and people in these decisions. The reason for that is it doesn't make sense to manage for carbon in some areas. It just does not. And we need to be measured as we think about what is the realistic potential of forests in the United States to mitigate climate change, and how much further can we push forests to contribute to offsets in emissions. We really need to think about reducing economy-wide emissions. And if we do that and we can at least maintain forests as forests, we will see their contribution increase because the overall economy-wide emissions decrease. Right now, the opposite is actually happening. We're seeing declines in economy-wide emissions, and the contributions of forests are remaining relatively stable, which means that the overall sink strength of forests is declining. So how can we sort of reverse that direction, or at least maintain what we've currently got? We need to do that while we consider the other ecosystem goods and services that we expect from these ecosystems.
What kind of like magnitude in climate change mitigation potential can we expect from nature-based solutions versus other climate change mitigation potential from like other sectors like energy, transportation? Like you had the slide that had the very importance of like the dot versus our total stock. So like where can we kind of expect NBS to fit into the grander scheme of things?
Yeah, it's a good question, and it's really very much regionally specific. I would say, we've done some studies that have asked the question. So, hey, for all understocked forest land in the U.S., there's right around 33 million hectares of understocked productive forest land in the U.S. If we were to fully stock those lands, and again, I'm not suggesting that it makes sense to do that in all cases, because some of those areas might be fire-prone ecosystems or other areas where it's a non-starter. But if we were to fully stock those stands and those trees grew as we projected them to grow, we could increase our sink strength, the sink strength of forests, by about 20% by fully stocking those understocked forest lands. Now, that's kind of a best case scenario. And again, that scenario doesn't make sense in all landscapes where, hey, a lot of ecosystems, particularly in the Western United States, look park-like. They absolutely are not fully stocked, and for good reason, because fire is a routine disturbance in those systems and has maintained those open sort of forest-like setting, park-like conditions where stocking is well below full, sort of that full stocking level. So I would say it really, the reason I start with that sort of point in that final slide where nature-based solutions need to be considered as part of a portfolio approach. Really what I mean by that is we need to look for ways to reduce emissions, number one. We need to think as a humanity, what are we willing to give up that will help us reduce our overall emissions? That is going to be less expensive than some of these alternatives. We've made generational investments in tree planting and protecting old and mature forests and a variety of other things, and enhancing existing forest land and reforestation activities and restoration activities that will absolutely help and hopefully can maintain or even enhance the sink to some extent. But we also must consider the other things in the economy in ways that we can reduce emissions. One of those within the land sector, again, is by substituting fossil fuels for renewable energy sources or renewable wood products, where we can use wood products in lieu of cement or steel or these other fossil fuel intensive building materials.
So just one last question here, and it is on the management side. So what can we do management-wise to either increase or maintain the strength of our forest carbon sink into the future?
Yeah, that's a great question. And it's a little bit loaded because I think, again, it's regional. And I don't want to punt on this one because I think a lot of the work that we are doing right now in our group, a lot of this community is focused on looking for ways that we can enhance the contribution of forests in the land more broadly. I think number one is look to nature. Don't 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 fight nature. So number one, where we've got natural reproduction, take advantage of that, harness that natural reproduction, promote that natural reproduction to the extent that we can. In other cases, go in, use prescribed fire. That represents some emissions, but let's use prescribed fire and other tools in the middle of these age class distributions. There are real opportunities early in stand development, those understock stands, to reforest and do things there. And there's a lot of carbon stored in our really old forests in the US. But the middle represents the greatest opportunity. Those forests that are 60 to 160 years old out there, a lot of those can be enhanced through silvicultural interventions, maintaining those forests as forests, utilizing. We can do everything right from a management perspective, and if we do something wrong in terms of how we utilize the wood, that can change everything. And so, thinking about the entire cycle of these forests, from establishment all the way to end product, is important as we think about their contributions to the atmosphere. So, looking at all age classes, there are opportunities to maintain and enhance forest land. But the biggest thing is make sure that we maintain forest as forest, number one.
Thank you. And I'd like to thank you again, Grant, once again for your time and information. Again, to all of the participants, the webinar recording and slides will be posted within a few days to be included on our mailing list, and to receive registration details and information regarding upcoming webinars. Please email forestc@msu.edu and stay tuned for the full 2023-24 lineup flyer. We'll be announcing it soon, and I hope you all have a great afternoon.